Hello and welcome to the latest webinar by Bick Gardner. My name is John Kowalski here from marketing. As always, I'd like to welcome you. Today's topic is a deep dive into media milling. This is the second in our two-part series. Last month, we took a deep dive into dispersion. I will place that YouTube link, that specific recording in the chat for you to look at if you're interested. This presentation is approximately 45 minutes long. We should have some time for some Q&A. If you have any questions, please drop them in the chat box. It should be in the right-hand corner, bottom right-hand corner of your screen, and we'll get to them time permitting. If for some reason we do run out of time, we'll follow up with you independently to make sure your questions are answered. Also note, we are recording this, so immediately following the presentation, you'll receive an automated link that will take you to the recording. Feel free to watch, listen later, share with colleagues, take some screenshots, whatever you like. Also, after the fact, if you do have any questions, you can simply hit reply to any of the marketing messages. It'll come to my team and we'll funnel them to the appropriate technical expert in your area. Today's presenter, Mr. Andy Stummer. He's the managing director of our VMA Getsman business. Andy, how are you, sir?
I'm doing great, John. Thank you.
Excellent, excellent. The floor is all yours. Take it away.
Thanks, John. Welcome, everybody. As John mentioned today, we're going to take a little deeper dive into the actual milling portion of the process. I think 3 weeks ago, we covered the dispersion part, which was actually the first part of this series. Okay, so with that, we'll do a quick introduction, just basically talk a little bit about VMA and the relationship with BIC. Then we're going to cover the dispersion process, just a recap. And then we're going to go into the milling component, and then we're going to close it out with some reviews on different types of lab as well as production equipment, and talk a little bit about the lab capabilities that we have here in North America at BIC USA, our sister company in Wallingford, Connecticut. Okay, so VMA is the company that makes the Dispermat. They were founded in 1972. They're still around. Herman still comes and visits the office about once a week. Design philosophy. And Bick Gardner has had a really good relationship with VMA dating back all the way to 1988. That's when we kind of became the exclusive distributor for the VMA Getsman product line in the US and Canada. The company is still owned by the family. The two sons, Martin and Christian Getsman, are the operating directors. They have over 100 employees worldwide. And VMA Getsman is known to make high-end dissolvers, speed mills, basket mills, not only for the lab space, but is also pilot and production units. So you can see the company's been around for just over 50 years, and the very first Dispermat was introduced in 1973. We still have some customers that are actually still working with the very old original Dispermats that they brought over to the US. And these units are still operating today. The motors are direct drive, so they're really good quality and haven't had any issues besides replacing the control panel. Okay, so here you can see kind of the aerial view of the facility. So they added on the building in the middle. There is an addition to the rear, close to that creek right there, that was added on, and they also added on another floor to basically add design capabilities and also make more space for building the machines. VMA is known to do a lot of customization, especially with those new end-use markets. You have batteries and fuel cells. So these new end-use markets require some customization. And so VMA is known to customize about 40% of all the equipment. And again, they have a complete solution for lab as well as pilot and production. And then we have a really nice laboratory to show the equipment in Wallingford, Connecticut, as well as in Germany at VMA. Okay, so the reason we are dispersing and milling is obviously we want to improve our product, so better wetting. These invisible electromagnetic forces, they're binding our pigment particles together. We want to break them up. They're called Van der Waals forces, with the goal, especially when we are milling, to reduce our particles down to primary particle size. So these aggregates, we want to break up the binding forces and then reduce them to the primary particle size. That will give us better color strength, better gloss, our overall appearance is improved. Of course, pigment efficiency is increased dramatically. That helps us save money on raw material costs. Products look better, so also better product consistency, formulation improvement, and more consistent particle size distribution. And also really important is really good upscale results from the lab to pilot all the way up to manufacturing. So if we don't do a good job dispersing or milling our material, we're going to have probably maybe a color shift, poor stability of our pigments, flocculation of pigments, sagging, leveling, settling, reduced gloss levels, and separation. It's just some of the issues that happen when we do an improper job dispersing or milling our material. So here's an example of a white color. So we have a Hegman grind gauge right there, and you can see on the left a pre-dispersed material, just using basically a cow's blade, and then stopping the process right there. And then on the right, you can see we continued then to move from a dissolver over to a bead mill, and then we were able to get a much better product, a much finer particle size distribution and finer particles. So it's really important that dispersing or pre-dispersing is only one part of the process, and milling is critical if we want to have really the best performing and best looking product. So critical there is obviously the stability. So pigments require strong color fastness to reduce fading over time. Brightness, the brighter obviously, the better our color. Pigment size, the smaller the pigment, that will give us a much better looking product. So that'll improve our transparency, color, and then again, cost is a big driver because it allows us to use less pigment because we are creating more surface area. Therefore, we're actually saving money. And that's also really important. And then another aspect is viscosity. We want to look at that we are in the optimum viscosity window. And that means we don't want to be too thick like a paste because it's very difficult to mill the material. And if we are too thin, then it's very difficult to put in a lot of energy. So we want to be in a good viscosity range, ideally 2,000 to 5,000 centipoise is optimum. That will also allow us to get a good looking donut when we are pre-dispersing. And then obviously when we are milling, we're able to put in the right amount of energy to break open these Van der Waals forces. So important to remember there is we are only trying to reduce the particle size and not destroy them. So we want to break up the binding forces and separate these particles and then basically keep them in a suspended state. So these agglomerates, we use a cow's blade, turn them into aggregates, and then from the aggregates down to the primary particle size is when we actually use the medium mills. And then really the shear forces are responsible for that separation of our pigments. And additives obviously are critical to keep those primary particles in a suspended state so they don't flocculate back together. and then we have to start all over again. So our sister company, Big USA, makes a really good different additives for different end-use applications. So we'll be glad to discuss this in more detail with you, with our Big Additives colleagues, if you have any challenges. Just a quick slide here to show you what these different pigments look like under a microscope. I always find it kind of interesting to see just the different versions of different pigments that are available. Okay, so the dispersion process is pretty simple. So these larger particle clusters, you can see that bigger circle on the bottom of that slide. These are your agglomerates. We wanted to turn them into aggregates. These are smaller clusters, and we would use a dissolver with a Cowles blade to get us from the agglomerate down to the aggregate cluster. If we want to go from the aggregate cluster down to primary particle size, is when we actually would use a media mill. And then again, we want to stabilize these particles in the suspended state. So this is a really nice slide kind of showing you kind of the process. So first, again, we start out with the dissolver. We're putting in a good amount of energy. We're wetting all of our pigment particles, and then we de-agglomerate them, and then we would move over to a media mill, where then we're able to go down to primary particle size and then stabilize these particles so they don't flocculate back together. Here you kind of see in this slide, like kind of the cutoff. So the dissolver obviously used to, as a first step, to de-agglomerate. The rule of thumb is about 10 to 30 microns of particle size, depending on the formulation, is what we're able to get to with the dissolver. If we want to go below 10 microns, is actually that's the point when we would start the milling process. So then we can, depending on the milling system, go sub-micron range and even down 50 nanometers and below with some, for some applications, for example, batteries, where they require, for these barrier coatings, where they require these very small fine particles. So with the right setup, we're able to actually get into these ranges. But critical here is that the cutoff is about 10 to 30 microns of particle size. That's when we should move over to a milling system. Okay, so it's always two steps. The pre-dispersion with the Cowles blade, critical number right there is the tip speed is 18 to 25 meters per second. That's the optimum dispersion window. For milling or fine dispersing, we run lower speeds, so 10 to 16 meters per second of rotor speed or milling disc speed. And there we have different types of media mills, right? So we have the vertical bead mills. Our system is called the APS. It's great for the lab space. It's called air pressure system. It's like a pot mill. We'll cover that in more detail a few slides down. We offer the basket mill approach, our TML or tourist mill, which is also scalable from laboratory to pilot and to manufacturing. And then we offer, obviously, the horizontal bead mill systems, the SL for our lab space, and then the RS series for the manufacturing size units. Just a recap for what's important is when we are pre-dispersing is the dissolver disc vessel size ratio. So there is not one blade that fits all different container sizes. So our rule of thumb is about 1/3 diameter of our blade should be the ratio to the vessel diameter. So if you look, for example, on this graph on the right, that table, let's take a 1 liter vessel. You can see that we can use a 30 millimeter blade for very low viscous materials, and then all the way up to a 70 millimeter blade for products that are really thick and viscous. But the sweet spot will probably be somewhere 50 to 40 millimeters of diameter. So that's kind of like the preferred diameter size. if we have an optimum viscosity to really get a good looking donut and put in the right amount of energy to predisperse our material. So we also have on our disper mats now, the newer models, the tip speed displayed on the graphical interface. So you can see that on the display. The only thing what you'd have to do is enter the right diameter of the dispersion blade that you would be using, or milling disc or rotor, and then it automatically would calculate the tip speed for you. So you no longer need to do it manually. But if you wanted to figure it out, if you have an older dissolver, it's pretty simple. All you would do is take your RPMs, multiply 3.14 by pi, and then times the diameter of your milling or cowl's blade disc, and then divide everything by 60. But you have to express the blade in meters. So if it's a 50 millimeter blade, you would use 0.05. And then times 3.14 times, let's say, 2,000 or 3,000 RPMs, and then you divide everything by 60, that would actually give you meters per second. And that's the value that we are looking for, to be anywhere between 18 to 25 when we are predispersing, but 10 to 16 meters per second when we are milling. So that's a good, important calculation. So you maybe want to write it down if it's not displayed on your dissolver or mill. Okay, the donut, obviously the visual cue, always nice to see that when we're predispersing. Here we can already see a really beautiful donut. The center of the blade is exposed, and then right around it where the edge of the blade is, the teeth, that's where we can see the donut being formed. Okay, so critical here is optimizing our predispersion results. So obviously the length of the predispersion process, so usually 15 to 30 minutes. If you go in larger batches, sometimes 45 minutes is reasonable. We want to ideally see the donut effect, but if you don't have it, doesn't mean you're not predispersing. It just basically means either your tip speed is not in the right range, or your viscosity is either too high or too low. When your viscosity is too low, like let's say like water, then it's very difficult for a donut to appear, because it would automatically collapse as soon as when it's trying to get formed, because there's not enough viscosity to really keep that donut going. And when it's too thick, then we also don't have a donut, because it's just, the viscosity is so high, it's just the blade will move there, but you never really see a donut. Doesn't mean that you are not predispersing. It just means that you're not seeing a donut for the viscosity reasons. So you can make some modifications maybe to your formula, or change maybe the blade diameter that you're using. Geometric consideration, obviously there's many different blade types and designs out there, so important to pick the right impeller disc depending on the viscosity, and then obviously the ratio, again, important to our container diameter. The fill volume, we recommend about 50 to 70% fill rate, as low as 40%. You want to be able to oscillate, and so if you go much less than that, it'll be more difficult to really, position the plate where you want it to be to get a proper donut or proper predispersion effect. If you're using a basket mill, for example, and you only have 40% fill rate, then you're really not able to move the basket around, in your mill base enough to really get the product pushed or moved into the basket. So you really want to ideally have at least 50 to 70%. Pigment filler concentration, obviously that's critical depending on your formula. We're putting in a lot of energy, so cooling is really critical. So especially when we are milling. So try to keep the temperature as low as possible. You're going to raise it up anyways if you're not cooling, because there is just so much energy that we're putting in that's then translated to heat. So we want to keep that container and the basket mill as cool as possible. Our basket mills have cooling jackets, as well as we highly recommend also using a double wall container when you're using a basket mill to ensure that we stay in the right optimum temperature range. On the horizontal mills, obviously, we also have a supply vessel where we have our product that can be cooled, and then the milling chamber itself has cooling jackets. So we are also cooling both supply vessel as well as the milling chamber. And again, additives are really critical, helping us smooth out the process and keep these products in a suspended state. Really important during the milling process that we have a really high quality additive. And then right particle size, again, 10 to 30 micron. It's kind of like the rule of thumb. And that's when we then start the milling cycle. So the differences between a dissolver with the cowl's blade and the bead mill are just that by using a cowl's blade, I'm somewhat limited in terms of energy input. I don't have beads. So therefore, we just rely on the teeth of the blade. That means limited amount of energy, limited shear force, and it's really only to deagglomerate. So it's the first step in the overall dispersion process. It's the pre-dispersion step, and it really allows us only to get to deagglomerate and go down to the aggregate level. Anything smaller, we really need to do the bead milling. Necessary step for any dispersion. We have some customers that think, hey, I have a bead mill, I'm just going to throw everything in a pot and then just run it through the mill. Most likely, you're going to have clogging of your screen or dynamic gap, and then you have to clean it out because the particles are stuck. So really important, always pre-disperse, wet out everything, and then go and move over to the bead mill. And as you had seen in one of the earlier slides, that Hegman drawdown example, you could see that the color strength is limited, and obviously all other sorts of appearance issues are there if you're not milling. With the bead mill, of course, we're going to be able to put in a lot more energy that is needed to really break down to the primary particle size, give us a much better looking product, better color strength, transparency, and obviously much better particle size distribution. Okay, so inside of a bead mill, what happens is obviously you have your beads that are circulating in the milling chamber at very high velocities, right? So as these beads are drifting towards each other, they actually create a shear force that is pushing your pigment particles away with very high force. And that basically is causing the breakup of these van der Waals forces. So that means that then these pigment particles get separated, these aggregates, and turn into smaller particle clusters. And with continued milling time, we're able to continually reduce those particles and make them smaller and smaller until we reach our desired particle size target. The shear force is really the most important part here. It's not that you're likely crushing the pigment. This is not the objective. Most of your pigments obviously will get pushed away from the beads, and that motion is causing these van der Waals forces to break up, not really the crushing. We want to destroy our pigments. Now, there is some impact grinding that takes place. Obviously, if you have a very high bead loading, it's inevitable that you will crush some of the particles, but the objective is not to destroy them, but to really just separate them out and return them to their previous original primary particle state. The principle here is very similar as when you maybe remember as a little kid and you were in a bathtub and your mom gave you a rubber duck and you were trying to catch the rubber duck with your hands by clapping your hands together. That rubber duck would always push away and very difficult to catch it. That's kind of exactly what's actually happening inside of a bead mill. So think of the beads as your hands and the pigment particle being the rubber duck. And then basically the beads are coming together at high velocities, and that pigment gets pushed away. That's exactly what's happening inside of a mill. So maybe that's an easy way to remember it, and it's always a little fun story. Okay, so media differences are also very important to look at, because some people use glass beads. They are relatively inexpensive, they're easy to purchase, and they prefer them over the zirconium oxide beads. But when we take a closer look at this tech sheet right there, you can see that the weight of the glass bead is, you know, less than half of what it would be with the zirconium oxide bead. Also, the hardness, right? You're only about a third the hardness of a good ceramic bead. So that kind of speaks volumes right there. So always try to get the better quality bead, because they're going to be heavier, giving you also higher kinetic energy, which would be really helpful when we're trying to break up these binding forces. So try to get beads that are heavy and ideally made of ceramic for that super hard surface. The glass breaks, it shards, then you're going to have uneven bead wear, uneven milling results, and then you would need to filter out those fines, these glass shards. So ideally, stay away from glass and always use the much better zirconium bead type that's available on the market. We sell those as well, but there are other suppliers out there where you can buy them. There's obviously different sizes available, so depending on what screen you're using, we use always our standard mesh size is 0.5, so we can use 1 to 1.2 millimeter beads, somewhere in that range. 1 to 1.7 would work fine, and that would really allow us to not clog up the screen and get good efficiency in the mill, and also have the product go through the screen with the dynamic gap, so we can continue our milling cycle. If you want to go to very, very fine particle sizes, then like low nano range, it's important that we then have to swap out our screen, use a smaller mesh size, and then basically allowing us to really efficiently mill those smaller particles. There's actually now newer type beads. We have them now that are as small as 0.1 millimeter for ultra fine particle size requirements. So they are also available. So here is a good slide kind of illustrating the influence or the importance of the bead weight relative to the kinetic energy. So think of it this way: you have a hammer like a watchmaker is using, they're small, only weigh about 50 grams, and you want to drive a nail in that board. It's going to take many blows for that nail to actually move, and you might actually never be able to drive it in the board. So what that means is if I increase the size of my hammer, I will reduce the amount of blows it takes to drive the nail in the board. Now, obviously, with a very big hammer, I only need maybe one impact. So that's kind of like the same idea. When we are milling, we want to use the right bead size with relative to the existing particle size, and always use the heavier beads to make sure that we put in the right amount of energy, helping us to break up these binding forces. Okay, so this is a formula. Maybe you just want to write it down. Kinetic energy, weight of the beads times the rotor speed squared divided by 2 is the calculation of the kinetic energy. So again, you can see the weight of the beads plays a really important role, as well as the rotor speed to determine the amount of energy you would be putting in to your mill base. So on this slide here, kind of like illustrating in another way of what happens inside of the mill. you have these larger circles. That would be your bead or your beads, your 3 beads. And the breaking up of these van der Waals forces is actually when the beads collide right in the corner, right there. You see that smaller particle cluster on the left in between those 2 beads, and then it gets pushed away, and then it reduces the particles to the smaller small particles that you see floating around. And that's exactly what's happening inside of the bead mill. It's the same in a horizontal bead mill versus a pot mill or even a basket mill. The principle is always the same. It's really the shearing of these clusters that helps us to break them open and reduce them to smaller sizes. So very important to remember is that the particle size after pre-dispersion with the dissolver should be 10 to 30 microns. Ideally, bead size and weight, again, this is due to the importance of the kinetic energy we want to put in, and the mesh size. Bead type, try to go with ceramic, not glass. There's different types of ceramic, so depending on what you're trying to mill, obviously the market is full of suppliers, and they will be glad to send out samples if you want to try different bead types. Bead volume, obviously dependent on the milling system. So if you're using a pop mill, a huge advantage there is you can add a lot of beads, up to 100% bead loading relative to your mill base, versus a basket mill has a much smaller volume of beads in the basket due to its design. But then there are other advantages. We'll cover that, just for example, scalability, right, which is very important to a lot of our customers. And then obviously the horizontal bead mills also have their own bead loading ratio depending on the size of the milling chamber. Shape of beads, very important. You want always to get the perfectly round or spherical beads, not the ones that look like footballs. We have seen those. They're relatively cheap to purchase, and then they will give you very poor milling results. Also be careful. We have seen some bead suppliers will offer samples that look really good under the microscope, and then when you buy your first lot, all of a sudden you see that there is all sorts of shapes in these larger lots that they sneak in there to keep the cost of the beads low. So very important, make sure you have high quality beads and that are also perfectly spherical. Again, I know I'm repeating myself here, but that's a really important parameter is the tip speed when we're milling, 10 to 16 meters per second, 18 to 25 when we are pre-dispersing. Product temperature, we're going to put in a lot of energy, as I mentioned earlier. It's very important that you have a high-powered or a good quality chiller that can keep up with the energy output of your mill or your dissolver with the basket mill attachment. So what you want to look at is that the chiller should have at least the same amount of energy output as the motor on the mill or the dissolver. So that's very important. So if the chiller is underpowered, eventually your product will heat up, and then you're not able to maintain the temperature range that you might need for a particular product. Then you have to stop the mill, cool everything down. So always look that the chiller has at least the same amount of energy output as the dissolver or the mill. The amount of energy we are putting into the milling process is very important. The number of passes, how often does it go through my mill or my basket mill or horizontal mill, the milling time, overall milling time, the resident time inside of my milling chamber, how long does it actually stay in contact with the beads, the viscosity of my mill base, again, 2 to 5,000 centipoise is optimum, but we can obviously work with different viscosity ranges. Unless it gets super thick, it might be an issue because the material still has to flow to properly go through the mill. Milling tool diameter, another variable, especially when we are scaling from lab to production, that becomes very important. The rotor material, our standard is stainless steel, but there's obviously zirconium or plastic rotors out there, depending on what you're trying to mill. And if there is any issue with bleeding off the steel into your slurry, like some white products, they require zirconium rotors because the steel would bleed in during extended milling times and then would kind of discolor your beautiful white product and make it gray. Or other issues would be cross-contamination of steel particles in an electrolyte, for example, for battery. That's an absolute no-go. So for these applications, selecting the right material for rotor and milling chamber is very, very important. And then obviously the different bead mill designs that are out there, vertical versus horizontal, depending on what you're milling and what the final target particle size target is. Okay, so with the Dispermat, we have some big advantages. If you are already using a Dispermat, probably you're very familiar with that modular design philosophy that Mr. Getsman had when he first designed the Dispermat. So basically, what he wanted was that customers would be able to use a standard Dispermat dissolver and then accessorize it with different milling attachments depending on the application. So what you're looking at right here is basically Dispermat CA, standard laboratory scale model with the quick change system, like a bayonet style, allowing you to also attach either an SR rotor stator, APS vertical bead mill or a pot mill, a CDS vacuum system. Some people like to disperse or mill under vacuum to remove any type of air bubbles, or to have a TML basket mill, as you see on the bottom right, and then also possibly a wall scraper unit for very thick and pasty materials. The ASC can be very helpful in these instances. So here is a close-up of the Dispermat right here that has the C controller. This is kind of like a really nice flagship control panel that we offer that gives you all the different variables to control the dispersion process, and then also being able to scale that to pilot and production. So you can run it with constant speed. You can also run it with constant power, allowing you to lock in, let's say, a certain amount of energy. Let's make up a number of 1,000 watts, for example. And then as your viscosity changes during the dispersing or milling process, the machine would automatically adjust the speed. So if your viscosity increases and you're locking in 1,000 watts of energy, then your speed would decrease. If your viscosity decreases, your speed would increase because you're maintaining 1,000 watts of energy. So that will also allow you now to precisely calculate the cost of manufacturing, because you know exactly how much energy the machine was using to disperse or mill a certain amount of material in a certain time frame. So that can be very helpful. The smaller models obviously have higher RPMs, allowing you to get to that critical tip speed of 18 to 25 meters per second, even when you're using super small blade diameters. Like some people have product volumes less than 100 milliliters, so they maybe want to use a 20 millimeter diameter dispersion blade. So you really need to have that 20,000 RPM to get you to that optimum dispersing range. And then again, these different attachments are available for all of our Dispermats. It's kind of like a trademark, and its importance is to the customer that he can buy basically one machine for many different applications. We also offer explosion-proof models where needed. If you're doing a lot of solvent materials or formulations with solvents, you may want to look at that. not only for lab, but also for pilot and plant size. Do we have explosion-proof models available? And then software is also available depending on the model that you choose. So in a summary, so modularity, important. This format can function as a standard homogenizer, or mixing tool where you can buy a propeller blade, butterfly blade. It can be used as an emulsifier, so basically as a rotor stator, and then as a standard disperser where we are breaking down these particles, where either we use the dissolver disc or milling disc or put on a basket mill depending on what we are trying to do, but basically very versatile piece of equipment. So here is a close-up of our basket mill, TML. Maybe if you're familiar with basket mills, there's many different designs out there. We believe that we want to have the entire basket double-walled and enclosed, so no screen on the side. That is because that's where we're putting in all of our energy, and the beads would impact the sidewall of the basket, leading to very high screen wear. And that's also where we would build up a lot of putting in a lot of energy and build up temperature. So that's why we want to cool that particular area of the basket. So that's why it's closed. And then on the bottom below the milling disc is actually where we have our screen. And then right outside the screen, we have a cowl's blade to help us draw the mill base out of the basket through the screen, basically keep the beads back inside, and then push the material or pump it back to the top of the mill, where then, as you can see on this picture right there is actually right above the milling disc is another disc. We call that the pumping wheel. And that has some small fins on top. And those fins are actually creating a vortex. And that vortex will then suck the mill base back into the mill. So that will help us really circulate our mill base very efficiently in and out of the basket with optimum cooling. Also very easy to clean. That's another big advantage of a basket mill over a horizontal bead mill. There is no leaking. There are no seals. There are no O-rings, no washers. So if you're familiar with the horizontal mills or three-roll mills, this is a much more efficient way of milling your material very quickly and effectively with low maintenance. There's another graph of kind of showing you the flow of the mill base in and out of the basket. So in this picture, you can actually see the beads on the left side and on the right. So they're located in the basket, and then they're only separated from the outside via that screen on the bottom. So that allows us then to, through the cowl's blade, to draw out the product, put it back, push it back to the top, and then that vortex will suck it back in. So we have a very good flow in and out of the basket of our mill base. Close up on a larger production scale basket mill. So here you can see there is a nut, hex nut right there. That actually is where you would put the beads into the milling chamber. So you'd use a feeding funnel, and then you weigh out the beads by volume, and then you just enter them right through that opening right there. So a TML is great because I can do the milling in the lab, but then I can scale that up to production and have almost a one-to-one upscale ratio, which is really, really nice, allowing me to really rely on the R&D data and then scale that up to production. Again, cleaning is so much easier on a basket mill versus a horizontal mill. That pumping wheel really helps us to move the product into the mill. It's pretty simple design, very easy to handle compared to other milling systems. Again, cooling, so important. That's why our design is double-walled. And then allowing you to use, depending on the mesh size of the screen, different media sizes depending on the final particle size. Here we have an example of two production scale Dispermat TMs, and they're unique in that they are actually a 2-in-1 system ready to go. So you basically have a basket mill design with a dissolver on the same machine. So the dissolver discs haven't been installed yet. They're leaning against the blue drum on the left, but they basically would go on the bottom of these shafts. So what happens here is this customer is producing a material, a pigment dispersion. He puts the container underneath the TM1000 with all his liquids, and then he's adding the pigment while the dissolver disc is spinning at low speeds, just to basically get the pigment introduced to the mill base. And then once all the product is introduced, he then increases the speed to about 18 meters per second, anywhere 18 to 25, and then does that for about 30 minutes. After that, he pushes a button on the control panel, and then the basket will come down, travel down along the shaft, and now you're turning this into a basket mill. So he never has to move the container to a different system. Everything can be done in one location, pre-dispersing, adding your materials, and then milling, which is a huge advantage over some existing production units where you actually have to move from dissolver over to a basket mill and then move the container again. So here everything can be done with one machine in one location. So that's a huge advantage also from a maintenance perspective, because you're only using one machine, not multiple machines for the entire process flow. So dissolver, basket mill, all in one, huge advantage, especially if you're running big movers like a white or a black color, right? Some of the customers do a lot of those, and they don't have to change, the color much on those machines. So they dedicate these machines to these big colors. The basket is fixed on here, so it's not easy to take off. So that would make it more complex if you have different color families. For that, we have that quick change system that also works in production, where you can actually use different basket mills for different color families, and then not tying down the equipment for extended periods for cleaning. We have the APS, as I mentioned earlier. That's our pot mill. That's great in the laboratory space. So what happens here is in an R&D setting, you may have to do a lot of different colors and trials. So you want to do very quick pre-dispersion and then milling. So you have basically a top container. The top container will hold your mill base. And initially, before you're milling, you would pre-disperse right into that container with the cow's blade. When you're ready to do milling, you replace the cow's blade and you just screw on a milling head. In this case, we have a double milling impeller, and turn the whole thing into a medium mill. You would also at that point add the beads to the container on top that has the mill base, and then you basically push down that cover that you can see here on the right with an air socket right on top of that cover. So that would allow you then to mill your material in a closed environment. When you are done milling, you would actually remove a drain plug on the bottom of the top container. There's a screen on the bottom, and then drain out the material into the container below. So the beads would actually stay back in the top container because the screen would keep them from falling out. But in order for us to do that more efficiently, we're able to hook up an air line, an air hose right to that socket, and now we are pressurizing that vessel and purging out the mill base with air pressure for an efficient transfer of our mill base out of that milling container into our collection container on the bottom. And then when we are cleaning, also very easy, we just put the drain plug back in place. we would fill our container 50% with cleaning fluid. We're closing it up again, and we are running it with the beads for a few minutes. We flush it out, rinse, repeat until it's pretty clean. So that actually allows us to efficiently clean that vertical bead mill without having to disassemble anything. We only would then eventually dump out the beads into a container and take off the milling disc and run it through a sonic bath for a few minutes, and that basically cleans everything. So very easy to handle and perfect for a laboratory environment, R&D setting, but not scalable. There is no large production versions of this available. The reason being, you can add a 100% bead loading, and that means, imagine if you have a production scale with a 1,000 liter product, you'd have to add 1 ton of beads, which would be extremely cost prohibitive and also very difficult to handle. So this is really only for lab, but not really scalable for production. So for that, the basket mill would be much better, or a horizontal bead mill if you have to use one. So again, the key here is it's a R&D system, 100% bead fill rate to mill base ratio, which is awesome because I get results very quickly. Ceramic option, it has a shaft sealing system. When we purge with air, different screen sizes are available. There is also an air pressure regulator that allows you then to precisely dial in the amount of pressure you need for your viscosity to remove the material. And again, it's super easy to clean. And we have container APS system all the way from 30 milliliters up to 7 liters of product. Again, not suitable for upscale or production environments. Here is a quick picture. You see the drain plug right there, how you remove that and then purge out the material. Okay, we also offer a series of horizontal bead mills, depending on the application. The basket mills are really efficient and work great all the way down to about 500 nanometers. Anything smaller than that, you would really need to use a horizontal bead mill. And for that, we have the SL for the lab, and then for production, the RS. The other advantage of a horizontal bead mill is that you can have a continuous process. That means you're running the material through the mill, it comes out, and then you basically are done. Or if you don't have the desired milling results or particle size, you would then add multiple mills in succession and then basically run them through until they come out with the desired particle size, giving you the ability to run a continuous process, which is kind of like a bottleneck of a basket mill where you have to a fixed container size. So this is a much better way if you have large volumes of product and you want to be continuous. But again, the SL or the horizontal medium mill, difficult to maintain, lots of parts, wear parts. You have your seals, you have your O-rings, you have all these wear components that need to be replaced periodically. And also you have the potential for leaking, which is not something that would happen with the basket mill. So there is no leaks there really. So this is only advisable if you want continuous mode and below 500 nanometers, and anything above that or not continuous, I highly recommend take a closer look at the TML basket mill. Then we have the lab space in Germany. If you have colleagues over there or a affiliate company that want to come in and do trials, we have everything ready for you to go there and review the equipment with your material. But we also offer the same in our Wallingford lab. We actually have additional capability there than you see on this picture, but all the basket mills, vacuum systems, a vertical bead mill with air pressure, also horizontal bead mills are in there. So we have 2 AE6s, what you see right there on the left with the different attachments, rotor stator basket mills, as well as the beautiful SL horizontal bead mill. So if you are in the market or you are interested in learning more about the equipment capabilities, let us know, and we would be glad to extend an invitation and have you come into our lab. So the lab space up there is actually located in Wallingford, Connecticut, at BIC USA, our additive sister company. So we can help you there to also optimize formulations if you have questions with respect to different additive packages, and leverage those synergies appropriately so that there is harmony between the instrument that you're buying and the additives that you're using. Nobody else offers kind of that turnkey solution, and that's the huge advantage what we offer here at BIC. If you're not in the market to upgrade or buy anything, that's also fine. Come by, just take a look, use it as a showroom, and review the equipment. We would actually be really happy to have you or some of your colleagues come by. And that's it for today. Appreciate everybody being on the call. Thank you.
Thanks, Andy. Good stuff as always. And yeah, that recording, Andy went through a ton of information, a lot of good formulas. So take a look at the recording and definitely take screenshots of it and use it in your facilities. We do have time for one question here. The question is, what is the percentage of production efficiency using the TML?
This is it's hard to give a ballpark number, to be honest, depending on what we are comparing it to.
Yeah.
We also need to look at the formula. What is the viscosity? What are the volumes? What is the final product? Also, what is your target particle size?
Sure.
Do we have to move to smaller beads? Are we good with the 1 to 1.2 millimeter beads? So there are a lot of variables that come into play. But I would have to say that when we do benchmarking and we're comparing, let's say, for standard pigment dispersions, and we're looking at it maybe, low micron range or 700-800 nanometers, we don't really see many differences between a horizontal bead mill versus a basket mill. But where we can say that differences are huge is when you compare a 3-roll mill to a basket mill. We have had an example that was recently where we had a customer reach out and they want to move away from the 3-roll mill. We had 2 products in particular. One was a maroon and one was a cobalt blue. And we were told by the customer that it would take them anywhere between 14 to 18 hours to mill these materials on their 3-roll mill. So when we had them come in the lab, we were able to do this in about 1.5 hours for both products.
Wow.
So needless to say, that blew, everything out of the water that they were using. And they were wondering why the hell didn't we move over to a basket mill a lot sooner? So that's an example of why it's so important to come to the lab. If you're running antiquated systems like this and you want to see the efficiency and performance of a basket mill, please let us know. We'll be glad to schedule that and prove it out, at no cost to you. The only thing we ask is that you are present when we do these trials.
Nice.
It's kind of shared ownership, because we travel in and we want to make sure that customer there is buy-in when we make that kind of commitment. So
great. Thanks, Andy, for mentioning that and addressing that. I think we can sneak in one quick question here, last one. What is the method you use to confirm the particles are stabilized properly?
So we actually have, in our lab, we just have a simple Hegman grind gauge to look at the particle size. If we want to look at particle size distribution and particle size, we have actually a particle size analyzer that we use. And then obviously milling efficiency is another critical one. We can definitely see the difference if we don't add, not on all formulas, so that's dependent. If we look at different formulas, we add an additive, a dispersing agent, for example, to keep the particles properly dispersed in the mill base, we would see that based on the milling results or milling efficiency. So we would take different samples at different time periods. And then I'm not totally sure what other evaluation methods that the additive team is using to maybe dive a little bit deeper into how effectively these particles stay dispersed during the process. But these are the parameters that we use.
Nice. Thank you for explaining that. All right. Thank you, Andy, for sharing your knowledge with us. Thank you, everyone out there, for attending. If you do have questions, if you'd like to get on the schedule and get to the Wallingford lab to test some of your material, any of the marketing messages, you can simply hit reply to or visit us at dispermat.com. You can reach us there too, and we'll be glad to help you out. So thank you again, and we look forward to seeing you on future Bic Gardner webinars. Have a great rest of your day.
Thank you very much.